All right, welcome to the presentation. We're going to be talking about Postgres high availability orchestrators. So it's going to be myself, Chris. I'm Chris Winslet. This is Josh Deare. If you don't care to listen to this, then you can just go straight to here and start playing with some code. I always like to give TLDRs for people that are just show me the code first and then I'll listen to you later, because honestly I'm that kind of a person. I don't like to sit in those kind of, I don't like to sit in the sales presentations where they talk about everything and then they keep everything at arm's length. It's like, show me first and then tell me. So TLDR, that's it. So what we'd built previously was a tool called Governor, and it relied on RAFT, consensus protocol, to get consistency. Now we're doing the next iteration of that. The previous iteration. Do we start a little early, Josh?
Yeah.
Did we? I thought we were starting at 10:20.
Yeah.
Okay.
Just rang the bell and then again.
Oh, sorry.
So
Okay.
wait like 2-3 more minutes or so.
Hey, you're going to have to listen to all that again, guys. Okay, the people who are on time. Okay. Let's give it 4 minutes then. Okay, for anyone, there's code down there at the github.com/compose governor/tree, and it's a Golang custom RAFT branch. If you want to monkey with that code at all.
Can I get this up and running in a Kubernetes cluster by 3 o'clock?
It's amazing how quickly you get the 80% done with that type of stuff.
Do I need anything other than just the Go base library?
Josh?
I don't think so. It should all be vendor. Okay.
Are you ready? Okay. All right, for the 3 people that saw this before, we started a little bit early previously. But all right. Okay, welcome. We're going to be talking about Postgres high availability with respect to the way we've done it at Compose. So there's kind of a couple of different bits to the title. Governor. Governor is a project that is a high availability project with Postgres. It's the way Compose, the company that I work for, built high availability for our database as a service Postgres offering. So it's the way we did high availability with Postgres. It's an orchestrator. We use RAFT. That's baked into etcd, so RAFT consensus protocol. We offloaded that onto etcd, which is a state store for consistency. I'm Chris Winslet. This is Josh Deare. Josh is going to be doing the second half of the presentation when we start talking about the technical bits. For the TLDR, I'm a programmer. When I go to presentations, I want to see code. I want to see how things work. I want to touch things immediately. And then I want to hear about how they work later. So if you're looking for actual code, you can go to github.com/compose/governor and then go to the Golang custom RAFT branch. We're actually going to be messing today. We're going to be working with both the master to kind of talk about how we currently do things, as well as this other branch to talk about how we're going to be doing things in the future. The way that this is such a change, we're actually going to be creating a new repo once we launch this. So Governor, the current state of Governor is going to, with the Python orchestrators, is going to be in this old existing repository, Compose Governor, and then we'll probably create a new repository called Go Governor for this new set of Go functionality. So I'm glad to do this presentation because we're going to be talking about how things currently work and where we're going and what we've kind of learned through the years of running this high availability system with Governor. Like I said, I'm Chris Winslet. I'm at Winslets on Twitter. If you go read it, there's nothing about technology there. It's just railing about election stuff lately, so it's not important. But you can send me a message though if you like. I work at Compose. I'm on the database team. We have a database team. We have a platform team. The platform builds the construct within builds the construct that the database is run within. So kind of think of the platform team as being the people who set up the Kubernetes, the orchestrators, although we don't use Kubernetes, you can think of it that way. And then the orchestrator for these containers. We use container-based systems for our database as a service. So I'm on the database team. What we work with is how can we maximize the uptime and maximize the use case for a database within this container system that our platform team has built. So that's kind of how we're structured there. Before, a long, long time ago, when I graduated college, I was a high school teacher for 2 years. So if anything happens, I'm ready for it. Like if lights go out, we can continue this presentation. Like there's nothing that that we'll just keep charging ahead. If you have any questions, just shout them out. We'll talk about the questions. If you don't feel comfortable, we'll have plenty of time for questions at the end. This is Josh Deare. Josh is one of those people that does not have Twitter. So if you want to talk to him, you have to talk to him in person today. And he's the brains behind a lot of the new technology bits that have been added. So what is Governor? Governor, you can go here and see what Governor is. It's an open source project for orchestrating high availability for Postgres. It serves as a template for how you might do high availability with Postgres. What we never said with Governor is that you should absolutely do Postgres this way. What we said is Compose's database as a service achieved high availability with Postgres. Here's the logical bits of how we did it. The reason we don't want to prescribe this method, we didn't want to push it on people, we didn't want to say this is how you should run it, is because we understand that there's a large world out there with a lot of different database needs, but that's how we did it within data centers. So if you want to judge, a project, judge it by its forks. One thing that I'm extremely proud of is the Patroni fork. So where governor is a template, Patroni is a deployment system. So governor works for the initialization and for the high availability. Patroni says, we're also going to include how you can think about backups. We're going to include how you should think about doing proxy. We're going to think about how you should launch within containers. It's actually a much full-fledged project about how you should launch Postgres. So while I worked on the governor bits, the high availability bits, I'm really excited about what other people have gone and done with some of the logical bits that we built there. So what is governor? Let's go back to that. Governor is basically a logic map. So it's a logic map about how a orchestration system for Postgres can interact with a state store. So I said etcd earlier. If you look in the logic map, you'll see the first thing we do from start is we connect to etcd. If you don't know what etcd is it's a RAFT-based consensus state store that we can use. So we offload a lot of the logic into etcd. So we offload the consensus and the high availability into etcd. So basically what we say is we have a Postgres cluster. That Postgres cluster stores its state information in etcd, which is going to have the consensus. So a part of the logic map, we connect to etcd. We say, after we get the connection, if the database directory is empty with etcd, what we actually try to do is we try to do a race. So we race to a certain initialization key that's set within governor. So once that race is either 1, then what happens is we initialize database. If it wins, then it takes over the lead TTL key and it starts Postgres, and then it starts a run loop down here. So this particular bit here is the PDF. If you want to go read more about it, it's in that governor repo. It's the PDF in that governor repo that talks about the logical startup process and the running loop. So the rest of that logic map that happens. So whenever governor starts, it always starts with the initialization loop. So it says, does Postgres need to be initialized? If Postgres does not need to be initialized, then it says, do I need to, can I just start on top of this data set that already exists? And it attempts to do that. After you get through the initialization loop, you start with the run loop. And basically, this is just a loop. So do I own the leader key? If yes, update the leader lock. Is Postgres the leader? If it's the leader, then it just goes to wait 30 seconds. So basically, you can think of it as just a dead man switch coming from a Postgres orchestrator. So it says, I'm still here, I'm still here, I'm still here. And then once that thing quits saying I'm still here, then the other members say, what happened to that? What happened to that person? How healthy was he? How healthy am I in relationship to how healthy it was? And then it tries to do some type of motion if it needs to. So that's the logical bits. So we're still kind of answering what is governor. Governor is Python orchestrators. It uses etcd as a RAFT consensus state store. It uses native Postgres streaming replication and a leader or follower configuration. And it provides automatic initialization, leader election, failover, and it attempts to provide refollow. So if a leader crashes, it attempts to provide a refollow once it comes back up. Because of the way Postgres timelines work, you can't always do that. So, like I said, I'm a demonstration kind of person. I need to see things working to fully understand what's happening. So I will try to do a demonstration. So here's what we got. So I've got three terminals here. If you can't see it, let me blow it up a little bit. 1, 2, 3, 4, 5. Okay, so we have three different things here, 3 different terminals. On this top terminal, we have governor.py, and then we're passing in a configuration file. Here we have governor.py, and we're passing in another configuration file that's going to be slightly different, that's based on this particular one. And then down here we have etcd. So etcd is that RAFT consensus state store that I was talking about. So let's take a look at let me fire this off, and then I'm going to kill the cluster, and then we're going to take a look at some of the configurations, and then I'll kick it off again. So if you remember that the top loop, the top of the initialization, basically what's happening is we always wait on etcd to run. So right now, etcd is not running because etcd is stopped. So the two governors up here are just waiting to try to connect to etcd. So let's try start up etcd. What we should see happening is this one won the race to initialization. So it's going to initialize. It initialized its database. Now it's starting the run loop. And then it's acting as a leader. This one has recognized that this leader came up, and so it synced the data, and it began following this other one. So let's talk about those configuration files real quick. Is that the right? No, that's the new one. OK, so this is the old configuration file. So every cluster gets a scope within etcd. That's basically just a path. Every cluster gets a TTL, so how long you want that, basically that dead man switch to stay alive. And then everyone has an endpoint, everyone has a timeout. Then we have the concept of a proxy status. At Compose, we chose Proxy as our portal. The reason we chose Proxy as our portal is our HA proxy it was the only one that we could reliably get to fail over and fail back over with very minimal prodding. So a lot of the ones that were Postgres specific, we didn't have much success with. So HA proxy, we used it. So basically we have a name for this Postgres. We give it a data directory. We tell it where it's going to listen. We give some replication information, and then we pass in some parameters down here. What we found when we're running this is everyone has different requirements. Some people want a synchronous replication. Some people are okay. Some people must have synchronous replication. Some people are okay with asynchronous replication. The people that choose a synchronous replication are ones who need better performance, maybe choose availability over consistency, and just those kind of, traditional cloud-based web platforms. Those are kind of more synchronous. Things that are more synchronous are, billing systems and that type of stuff. So what we found when we were doing research, even after we built this, was that you can do synchronous commit local, and then you could do synchronous standby names, splat. And with this, what you can actually do is change that on the fly with a per connection basis with Postgres. So what we've told our customers who need that synchronous connection, we've said, here, just set, when you connect, set synchronous commit to remote. And what will happen is you'll get synchronous commits across your cluster from any particular connection that you want to achieve that on. So we're actually quite happy with the ability to be able to launch, as a database as a service product, the ability to be able to launch a standard system that our customers could then modify their use to get what they want out of it. So these are the parameters. And these parameters are applied to Postgres as it starts up. So let's see if that high availability will actually work now. So this is where you make the money. So we have the leader here. Let's kill the leader. So what happens is invalid record length. It was streaming that replication. The replication stream died. It says no action. I'm a secondary and I'm following a leader. Little does it know that the other leader died. The etcd TTL hasn't been killed yet. So what should happen is on the next loop, this one should say, okay, so now we're seeing issues connecting to the server. And what should happen in a second is that this one has been promoted. So promoted self to leader by acquiring session lock. Basically, that other dead man switch has died. And so now it is running as a leader. So previously, this one was running as a leader. Now this one's running as a leader. I'm running 2 nodes here. The way this configuration works, you could create a Postgres 3, Postgres 4, Postgres 1,000. How many ever reasonable number of replicas that you want to run. You can have that entire cluster. And then what happens is, if we start that back up, so this was actually kind of okay, so I'm a secondary and I'm following a leader. So we're making an assumption here that the timeline did not change, that this one accepted no writes. So in the case of a network partition where this one may have been branched off and then had its own clean shutdown that didn't get pushed up to the leader before it got pushed off. In that case, we'd have a split timeline. That's where our maximum, so that's where this particular configuration setting comes in. Maximum lag on failover. What we say here is basically, if you're using a synchronous commit, if you're using a synchronous replication, then you have to accept some amount of data loss on a failover. It's going to happen. If you're using synchronous commits, then data loss, like using synchronous commits where it's synced to the cluster, then you're expecting to have no data loss. What you should have failed writes in the event of a failure. So this maximum lag on failover, if you're using asynchronous, if that leader gets branched off, then it'll have timeline issues. So anyhow, that's a little bit in depth. Anyhow, you can go play with that code. There's a couple of copy and paste there within Governor. That's how Governor works. Any questions about that?
Yeah, sure.
Okay.
So your first standby that took over, if both of them shut down and restarted, is there something in etcd that tells which has the later timeline?
That's a great question. No, it's not in etcd, but we baked it into Governor. So so what we're doing is we're storing, in etcd, we store the wall log position of the leader. And we say so every time that loop runs, we say, where's the leader? Let's store that wall log. Where's the leader? Let's store that wall log. And so then, once a secondary comes up, and there's no leader, if a secondary comes up, there's no leader, what happens is Governor compares the position of that wall log against the one that was stored lastly by the Governor for the leader. And if it's within that maximum lag on failover, then it will promote itself as leader. But if it's not within that range, it will never promote itself. So that's just kind of it's just a make sure something, I guess, adjust that figure for your use case. You know, I mean, some people say, some people may be pumping so much data through Postgres that, losing 100 megs is insignificant. Some people may say, I need every single bit. So they may have 0, so it's just kind of, does that make sense? Does that answer your question? I mean, we offload so if you have 1,000 nodes, a 1,000-node Postgres cluster, which is kind of, I mean, that's extraordinary, I guess. But if you have a 1,000-node Postgres cluster, you have governors running on every single one of those Postgres, you're connecting to a single etcd, I mean, it should work. Like, it should be fine. We're offloading all the consistency onto etcd more than trying to manage it internally. So there is that still single point of connection. So it should work.
Question?
Go ahead.
If the etcd itself dies, so what's going to happen?
Okay, you're getting ahead of me. Okay. So the next slide after the demonstration is, where's the weak point? So where's the weak point? Ideally, etcd being RAFT, it is highly available by default. So it is a system that is built to be a cluster by default. So it is a system that is built to be highly available. And basically what we say is Postgres is not built to be highly available by default, so let's go rely on a system that is highly available, which is etcd. So, but where are the weak points? So demonstration of failure. Let's see. Okay. So what we have here is I've just killed etcd. What happens with these two things is on the next loop, they can't connect to etcd, so we send them into read-only mode. This was very logical here, the way that I just killed etcd. It's like, of course you can't connect. Go read-only. In a cloud environment, you don't know why you can't connect to etcd sometimes. Sometimes you can't connect because the network doesn't work. Sometimes you can't connect because the etcd server may be getting some, some just having issues as a whole on that host. So it's kind of, it becomes much more unpredictable in the cloud, and it becomes much more unpredictable once you scale out to the size of a database as a service company. Like what you said, like what Craig said this morning, Craig Kierskin, he said, when things are 1 of a million chance happening, then when you have a million things happening, expect those 1 of a million events. You know what I mean? And that's kind of where we are with this next iteration. It really helped us improve the high availability of Postgres, but we're starting to see these little patterns that where our connections to etcd are either etcd is not responding or something like that becomes a problem. And so that's why we're talking about this. How do we deal with that? So failure starts when you can't trust the response from etcd. So if you remember that logic map, what I said is we're offloading all the consistency logic onto etcd. So all the governors are really just Postgres orchestrators that rely on something else to do the consistency. So we chose a very simple approach initially, and we said, governor is going to figure out how to manipulate Postgres to get it to run as a cluster. We're going to just offload the consistency to etcd. And so let's look at, so failure starts when you can't trust the response from etcd because etcd is truly baked into this logic map. If you look at our logic map that we pulled up earlier, where are we connecting to our state store? We're connecting here, we're connecting here, we're connecting here, we connect down here. So this happens just on initialization. And then once we come back up, each time it loops through, we're connecting right off the bat, we're connecting here, here, and then based on this branch, at most you can have 3 interactions with etcd on a loop. And then even one that I said, one that is not up here was storing the latest state of the leader member. So it's kind of, we're very much relying on etcd. Now the problem isn't etcd. The problem is the system that we work within. We're working within clouds. We're working within data centers that we don't necessarily control. We don't control the network of it. We can monitor it, but we don't necessarily control the network. So someone else is responsible for the network. We, as the database member, as the database team, have to figure out how to run within these systems that we are given. And so the problem isn't etcd, it's how we connect to etcd. So HTTP was built, so you connect to etcd with HTTP. HTTP was built to accept failures. However, our system cannot accept failures. We have to rely on the consistency of etcd. So once you start saying there's an etcd failure, should you retry? Once you start that retry, then you're automatically introducing a race condition. Not necessarily a race condition. Yeah, you're introducing a race condition where it's something else. So once you fail and retry, something else could come in and capture that leader lock while your system is still trying to retry connecting etcd. So it's once we stopped, and honestly, like at Compose, to get some things to kind of work properly in the cloud, we had to put in those retries, but we realized those retries were not the right way. You know, it's like these retries we're putting here because it reduced the number of failures that we have within our clusters. However, there's a better way to solve this other than introduce these retries. So the retries were really a stopgap, but we did not feel that those were the best way to do this. So then the larger problem becomes, if you're running multiple clusters off of an etcd, so you can run many different, you can change that scope that I talked about earlier. You can change that scope, and then within that scope, you can run multiple different database clusters off of one etcd deployment. So then you have a governor here, governor here, governor here, governor here. All these you can think of as their own deployments. Now the issue becomes, once that etcd cluster gets overwhelmed, gets overloaded, network's not working properly, whatever it is, everything falls over. It's like you have everything falls over at once. And the good thing about the way we built the high availability is you get a leader to come back up very quickly. So once that etcd restores connection, you get a leader to come back up very quickly because that's what we built. We built a high availability system. However, you had that short amount of downtime, and then what you also have is you have a mess to clean up. And that mess to clean up is all the other timelines that may have gotten out of sync around all those other nodes that were relying on that connection to etcd. So that RAFT, with the RAFT protocol, these are the people, these are the governor deployments, they're all getting dumped over. So everyone gets ejected. All the leaders get ejected. So the solution that we have, and you could probably see that from the title of the presentation, was now with RAFT baked in. Now we have one RAFT per cluster. So by baking in a RAFT into this governor, we can start talking about how we can have the state store right next to the database, right next to the orchestrator. And so then we're reducing our reliance on etcd. The story that I tell myself about why this is the next best step is because previously what we did is we offloaded the complexity to etcd while we figured out how to manipulate Postgres. And then we did a very good job of manipulating Postgres to keep high availability, to keep these clusters up. But then the next step to be able to get even more high availability is to take on that bit of complexity. So the trade-off is complexity. So what we had previously seemed hard in the beginning, as far as the orchestration of Postgres. It seems simple now in recollection, so we took something that was complex, made it simple, and now our next bit is taking the complexity that is the RAFT bit and try to bake that into governor. And now, so that's all the old governor, and that's where we're going to go. But I'm not the one who did that bit. I did the old governor stuff, and I got it working. And then after you build a product, you have to maintain it. So I've been working on maintaining, our current systems. And so Josh is going to talk about the new bits and kind of the process that we got to about how we got to where we currently are. Josh.
Alrighty, where are we now? All right, cool. So the first step when we realized that we wanted to bake RAFT in was kind of research what was out there. RAFT was published as an easy to implement consensus algorithm, but it's still very, very non-trivial to implement properly. And so we wanted to look out there and see what already existed. The first thing that we wanted to do was see which language currently has the best RAFT implementation in it. So no use using Python if there's no good RAFT implementations written in Python. Well, big surprise, there's not. And so we found that Go was really the only one with any mature RAFT projects, RAFT libraries already, at least at the time. And so there were two main ones. The RAFT library that etcd uses, which is buried inside of the etcd repository. From now on, we can call that etcd RAFT. And then there was another one written by HashiCorp. And the etcd RAFT is used only by, it's used by etcd. It's also used by, I believe, CockroachDB and then Docker Swarm. And then HashiCorp is used by Console, and they might use it in one other product, but I can't remember off the top of my head which one that is. So we went through and prototyped with both of these RAFT libraries, doing just some really simple stuff. I think I ended up writing a KV store, a key value store application that's kind of the hello world of the RAFT world. And what we found was the etcd RAFT library was very, very featureful, but it was a pain to work with. If I remember properly, to get just the most simple key value store application written, it was about 350 lines of code. and even then, it didn't use all of the features that it could have. It didn't have snapshotting. It didn't have on-disk while. It didn't have just a lot of stuff. And with the HashiCorp RAFT library, it had a really easy to use interface, and it was really, really easy to get started with, but it just lacked a lot of features that we would want in Governor for a RAFT library. So out of that, we needed to decide what we were going to do. And we decided that the best route was to combine these two and to kind of bake our own. So what we decided to do is we decided to abstract the etcd RAFT library. So we wrote a thing called Canoe that's right down here, and it's kind of a new RAFT library. To emphasize, we didn't write RAFT from the ground up. We used etcd RAFT, and then we added a wrapper around that to give it kind of the interface that HashiCorp gives. So we wanted the interface that we got from HashiCorp, and then a lot of the features that we get with etcd RAFT. One of the big ones with etcd RAFT is they kind of add an addendum onto the RAFT protocol to try and get better guarantees to ensure that when you propose to apply a log to RAFT, then it makes it so it's more guaranteed than normal to get successfully applied. The other thing that we wanted that came in neither of these libraries was dynamic runtime configuration changes. As it stood with these two, it was a very manual process if you wanted to add or remove a new node to a RAFT cluster. And so with Canoe, it kind of has those constructs built in. So in the arguments you can give it like a list of peers and some bootstrap options, and it'll automatically handle the addition of itself into an existing cluster. And then so I would love to talk about Canoe more, but that could be an entire talk in and of itself. So I'll just get into how we used Canoe to add it into Governor, into the logic flow. For the most part, the logic itself is very, very similar to what it used to be, but now we've defined a state machine and backed it by RAFT inside of Governor. The big difference is, if you remember, whenever we were showing that failover scenario earlier in the demo, it took about 30 seconds or so, 20 to 30 seconds for that leader, for whenever you killed a leader, for a new node to come up and take leader. With using Go, we were able to use more of a subscription pub sub-ish kind of model where you could subscribe to events, and then so as soon as a node goes down, then you're subscribed to the event and it'll come up. So you're using like a pub sub versus a polling type of method for updates on the state of the cluster. Alrighty, Chris, you want to come up here and drive demo? See, how are we doing on time? Do we have time to go over that config file?
11:15. Yeah.
Yeah, okay, cool. Yeah, so I'll bring up one of the config files. If you could bring up not Postgres 0, but Postgres 1 config file. So we can just see a little bit of how the config file changes. Oh, well, I can just explain it. So we do still have a loop that runs inside of the new Governor, but that's mostly a loop, more of like a backup. Has something gone horribly wrong that for some reason we weren't subscribed to a right event or something, so it does auto-correction in case something's gone wrong in that subscription model. Then where is, oh, cool. We have the data directory is the same. We have an API port, which Governor now has an API built in that'll give you cluster health information. That's kind of a work in progress right now, but it does basic things like who is the leader, which node should a proxy go to, and such like that. We have
Cluster ID commented out.
cluster ID. Oh, cluster ID, so that is an option that is a part of Canoe that if you wanted to, you could specify cluster ID and is kind of a backup safety to make sure you're not accidentally joining the wrong cluster. So for now, we're not using it, but it's an option, and if you specify the wrong cluster ID by accident, then it'll just error out and not connect to that cluster. Then we have leader and member TTL. So if that's kind of if something goes horrifically wrong in this cluster and a governor isn't properly reporting the status of its underlying Postgres process, then this timeout will come in and all of the other nodes will then get informed, kind of like a dead man switch like the old version. So this is just kind of a fallback for, again, if something's not detecting on that subscription model properly. Then we have kind of everything down here is basically the same, so we can move on to a live demo. Alrighty. So here we're running the first node of the cluster, and then just wait for that to come up. So it's initializing. It won the initialization race at 1, and Chris, oh, you need to kill your other ones.
Okay.
Yep.
So that was a poor conflict.
And then, yeah, go back there, remove the data directory. Right. Yeah, cool.
Let's start it. Okay.
Alrighty, sweet. So run the first node. We don't have to wait for this one to start running, but I just want to get it going so I can point it out with other things not getting in the way. So yeah, we won the initialization race. We're initializing, starting Postgres. We're running as leader. As you saw there, it was adding itself as a member into the RAFT state store. And then if you want to just boot up the other ones. And then so these will come up. They'll connect to the RAFT cluster. You'll see some things up here, RAFT-y things about those new nodes connecting. They're both running as followers now, and they've added themselves into the state store as well. If you want to go kill the leader so we can see what a failover looks like. So we've killed the leader, and then this has already failed over and elected a new leader and a follower over here, which is a lot faster due to that subscription model like I was talking about. And then with RAFT, so you have to have a quorum of nodes active in order for RAFT to function properly and be able to apply new logs to the RAFT. And so in this scenario, if we were to kill another one of these nodes, then the state would basically lock and nothing would really happen, and you'd have to bring up another one of these. So basically, in order for this to work properly, you need to maintain a quorum of nodes. If you want to bring back that one to show it coming up as a follower.
So wait, so we could kill node number 2 and then replace node number 2?
Yeah, so what we can do here is if we kill, so say we kill two nodes and then we lose quorum, then the state of this would lock, and the things you would have to do is you can either bring node 2 back up, in which it will rejoin the cluster, then you'll have 2 of 3 nodes, so you'll have quorum again. Or what you can do is with Canoe, there's a utility called Captain, where you can point Captain to a node in a Canoe cluster and then do a deletion of it.
Yeah, that's where the complexity comes in.
Right, I was going to say, right, before I dive more into this,
Mhm.
let's let you finish your presentation.
Okay.
Okay.
Well, I think that's actually about
Yeah,
it.
I
I think
mean-
we're going into questions now.
Right,
So.
yeah.
The last slide is questions, and we are hiring.
Okay. What was the, yeah, because then I have a question is,
Mhm.
when you say bring node 2 back up,
Yes.
is that checking for something that this is actually the original node 2, or maybe that I brought up a new node and I just called it node 2?
Yes. So Canoe generates a UUID for each node. So it's based off of that UUID.
Okay. Okay, right, so if I was replacing node 2, it would still not count unless I called Captain.
Correct. Yeah.
I have a bunch of detailed questions about the config file.
Oh yeah, for sure.
I'm trying to build a container right now.
Got it. Yeah. And there's a few gotchas with. So Canoe is also currently a work in progress, and we're working to add some improvements to Canoe, which will therefore add new improvements to here for as far as the configuration is going. But
Yeah, what was really, I tried to lay out the story of what was very nice about the previous configuration was that we could offload the complexity. Basically, we became Postgres orchestrators, and something else handled the state. We recognize, like, with this change, there's going to be a fair amount of testing and a fair amount. We're trying to get to that next bit of availability that we're missing just through connectivity issues, not being able to trust the connection to etcd all the time. So we're going to be launching this with our 9.6, but we're also going to be measuring it and making sure that it's achieving the availability that is better than what we previously had.
So just a question.
Mhm.
So now, instead of relying a CD for just running the daemon, now you have actually distributed the orchestration of that to each node, and then using the custom RAFT protocol, you are relying on that cluster in and of itself to make sure that there is enough quorum and enough leader. Enough quorum so that there's a leader, and then is that how you're doing that right now?
Yes, so the way GNU is written is you really don't have to know all of the specifics of how RAFT works. So it doesn't matter who's the RAFT leader in this case. Like you have a RAFT cluster, all you need to know is you have a RAFT cluster and you can propose new logs to this RAFT cluster. Like built on top of that is a state store level, which stores things like who is the current leader, what are members underneath that leader, what are the while positions of some of these members and connection strings. Mm-hmm.
So the GNU agent is running co-resident with the Postgres. Is that right?
Yeah, so it's GNU is just a native Go library, so GNU is imported in this Go code.
Okay, so
Yep.
in this case, if say the leader and one of the followers were killed,
Mhm.
that would mean that the remaining follower would not have quorum to be able to propose itself to become the new leader.
Correct. Yeah, it would default to read only.
So you would have to go in and manually intervene to force it to say this is the only thing that lives. You are the hope of humanity.
Yes. Yeah. Exactly.
Another question. Isn't that the choice of, let's say the quorum is gone,
Mm-hmm.
there's only one node, right?
Yeah.
And then you default to read only. Is that the choice sounds sensible? Because, let's say it's running an application, and if there's no write, my application is just gonna collapse.
Yeah.
It's something that you involve, like, hey, I'm only running one node, and some human intervention is needed
Mm-hmm.
to bring up the other clusters.
Yeah.
What do you guys think about that?
That is something that, so with RAFT, so if a node loses quorum, you don't know as that node, you don't know, is this because the other nodes died, or is this because I'm having issues with my network connection? You don't know if it's a problem with you or a problem with the rest of the cluster. So if you as a node say you lose your quorum, you have you're not able to safely say, I should elect myself as a leader, because at that point then you're introducing timeline conflicts. You have the possibility to be introducing timeline conflicts, because you could separate yourself. Say you have a 3-node cluster, one node could lose network connectivity. If that node says, hey, I want to be a leader, but there's already a leader on that existing 2-node cluster still, then that's going to be split brain, I think. But yeah, but.
So that brings up another question where you clustering it, and there's a proxy sitting between this and application.
Mm-hmm.
That means you have to make sure that you don't forward any write to the read-only node, right?
Correct. So yeah,
How
so.
it is done?
Yeah, so if you noticed in the config there is an API port, so each governor node can report if the underlying Postgres process under it should be accepting writes, and based off of that, then you can determine where the proxy should be pointing.
So you start up one node that's the bootstrap node.
Yes.
And so then how do the other nodes, assuming that we have like an ecosystem with multiple clusters in it,
Yeah.
how do the other nodes know which bootstrap to join?
You have to tell them.
Okay, so which parameter is that?
Okay, so for the bootstrap node, you have is bootstrap true over here for the initial bootstrap node, and then you don't give it a list of any peers. And then so that node just comes up and it becomes its own single node RAFT cluster, and then over here you point it to that single node RAFT cluster. That's one of the improvements to GNU that's coming. Is if you're familiar with etcd, there's an initial cluster argument. So what we would like to do after we add that to GNU is be able to just say, instead of having like an is bootstrap node type of thing, then you just tell it, these 3 nodes of the initial cluster do not start RAFT and do not start anything until that entire cluster has talked to each other and agreed that they're all a part of that cluster.
So with his Kubernetes deployment, I would want to integrate the service discovery with something like SkyDNS or something outside.
Possibly. I'm not that familiar with Kubernetes personally, though. So.
Josh can probably answer that far better than we can.
Yeah, how do you propose for the clients to find the master?
Yeah, well, that's what I'm writing right now, actually. So that's actually relatively easy, and just attend my session at 3:30 or whatever it is, with the new stateful setup. It actually makes that fairly simple. And then you just pass along, you tell it which set it's part of, and then it's fairly easy for it to find the master. So and maybe I will actually get this particular, maybe I'll get governor working before 3 o'clock. We'll see.
Can you go into more detail about where HA proxy is living in the system?
Yeah, well, right now it's living nowhere. So in our deployment hierarchy, which we haven't launched this onto our system at Compose yet, but how it would look like is you would have a 3-node, like you would have a 3-node Postgres cluster, which would be on its own private VLAN, and then you would have an HA proxy that is another container that it's an ingress point, so it has a port exposed to the public net, and then it'll proxy that through to the cluster, and then that hub proxy can then query like a hub proxy status server that is running on each of the Postgres nodes.
And that's the way we've chosen within our infrastructure to do it, because that's the way our platform works.
Yeah.
We don't use Kubernetes, and we don't use like a DNS to route to a leader like you might in a Kubernetes environment.
Yeah.
Well, we actually have our static IPs for VLANs within our platform, and so those static IPs. So then we have a proxy that sits out in front and connects to these static set of IPs that are known.
Yeah, and if you want to roll your own, like using, something other than HA proxy or something like that, then you can just use the health check endpoints on the Governor API. Right now, this hub proxy status option right here, that Governor ignores that. It's not a part of Governor. It's if you want to pass this same config to a hub proxy status script that we have written in Python.
So it seems like a lot of infrastructure to have a single point of failure just move to HA proxy. That's something we're working on right now. So what we want to do is we want to have 2 hub proxy nodes in front of a Postgres deployment. The problem is that for most, if not all of the drivers for Postgres, they only accept a single node connection string. So what we're going to do is we're looking into having DNS failover.
And along those lines too, it's like saying that kind of discounts the number one reason for database outage, and that's some type of maintenance on the host. And so we can do failovers without having to worry about systems. So we can do failovers and do the maintenance that we need to be able to do on the back end. Very few outages happen because of outage.
So I say like the new project is written to go like the old one was in Python. Going forward, are we kind of maintain both, or just going to?
Yes and no. So as Chris said earlier, the old Python version is going to stay on the Governor repo, and the new version, once it's kind of finalized and tested a little bit more, will go onto the Go Governor repo. We'll create a new repo for it. We probably won't actively maintain the old version, but we'll still accept PRs against it.
Well, I would argue that Governor was just the template, and Patroni is something that it's like the template that is there is going to stay there. It's going to stay simple the way it is simple, so that people can build on top of it if they want to build on top of it. So we're going to keep that simple, and then I absolutely love what the guys did at Patroni, because they were trying to get us to do some stuff to Governor, and we're just like, we aren't going to do that, and they were like, okay, we'll fork it, and we're like, perfect, and it's far better than what we could have built for people outside of our ecosystem. So long story short, if you're looking for something that's a maintainable, deployable solution today, go check out Patroni. If you're looking for a template, go check out Governor. If you're looking for what's kind of happening next, watch the Go Governor stuff. All right. Well, thank you so much.
Thank you.